Welcome to Swayam Prabha series in computer science, and this is a course on artificial intelligence, and we are in module unit 5 of module 28 where we are looking at natural language processing techniques. And in natural language processing, last class we saw about statistical NLP, where we found out the probability, the foundation of probability, and how probability is being used inside natural language processing. And today we will be continuing with that, in the sense that we will be discussing on the smoothing techniques, where in some cases it might be 0. So in order to avoid 0, how we are going to play with it so that it's not actually 0 but some other values. So and that's the first part, which is the smoothing. And then we will move into two other techniques, which is the TF and IDF and cosine similarity, and we will be dealing that in today's session. Yeah, so the topics as such, where we are, you can be seeing in this slide, where in the first part we saw about the syntactic structure of natural language processing, and then in semantics we understood the meaning of the sentence, and in syntax it was only about the vocabulary and the sentence structure formation, like example the parse trees that we constructed, which does not construe any meaning, but it was aligning with the structures per se with respect to subject, verb, object, and with respect to the parse trees or the part of speech. Now in semantics there was more into the meaning of the sentences, but on the words particularly. And much more deeper we went into the statistical base of NLP, where it was mostly the probabilistic driven. And in the last class we were at this slide where we had the probability measures, and we discussed about the bigram and also a little bit about the sentence modeling using those measures. And today we will be dealing into these two structures, which is the sentence modeling and solving NLP task, and particularly what we would be seeing is how words are represented numerically. And in that numeric sense we will be discussing with two things. One is TF-IDF and another one would be cosine similarity, and both we will be using it for further calculations and further understanding of the sentence. And in today's LLM these are being used, so I would spend some time on this and get into the modern neural NLP, which will be after one or two sessions. Now this is our overview of what we saw last time. Here is one example, the same type of example that I have taken from last time. The first example is I drink tea. Second example, I like tea. Third example, they drink coffee. And if you see these three statements, this is S1, just S2 and S3, just the statement. See S1, S2, S3. We have drink tea as a bigram, the count is 1, like tea a bigram and the count is 1, drink coffee a count is 1, and if you see drink alone the count is going to be 2. So I am just write count of drink is equal to 2, because here we have one drink, another drink is at third. So for this, if we compute the bigram probability like last time we discussed probability of milk given drink, which is the conditional probability, and using bigram probability of Wi given Wi minus 1. If we calculate that probability, it is count of the word I minus 1 as that appearing before the particular word Wi, and the count of Wi minus 1. In this case, how many times Wi is the drink, sorry, milk given drink. So how many times drink is appearing, that comes at the denominator, and Wi is milk. How many times milk comes at say before drink, and also the drink. So how many times milk drink is coming within the whole set of documents that is given here. So in this case, milk given drink, where the count Wi minus 1 and Wi drink milk, it does not appear inside this statement list, in this case, the probability is going to be 0. So the count of drink milk is 0 in this case, because there is no occurrences within these three statements. Again, assume that it is only we are checking within these three statements, but not in the entire literature per se. In the corpus, some other places there might be drink milk, but that is not accounted. We are taking only within these three statements. And count of drink we have counted to be 2. Therefore, this probability of milk given drink is actually 0 by 2, it is 0. Now, this 0, it is very ambiguous. The reason is, if you take it as a full probability, suppose you take this S3 structure, probability of drink given day multiplied by probability of milk given drink, then this probability is going to be 0. Why? Because this we have calculated as 0, and drink given day, it is actually, there is a count of drink given day. We can have this as a probability of Wi minus 1 and Wi. This is not actually equal to 0 here, but anything not equal to 0 into 0, this is going to be 0. So this sentence, the whole, if you take the whole probability, it is 0. Although this English statement is valid and there might be some other occurrence of milk somewhere else, but still even this is not accounted here. So this actually poses a problem when we have an entire calculation as such. So in order to avoid this, we will be using smoothing techniques. So that smoothing, it is not that this statement will be not unseen, but if it is unseen, it takes it at 0, but it is actually not impossible. It is only unseen. There is a difference between impossible and unseen. So although 0, it might appear somewhere else. So how do we account for that possibility? So that possibility comes with the help of the smoothing techniques. So the easiest and the starting method of smoothing techniques is the Laplace method, where we will take the same example and compute the structure with the smoothing technique as such. So take the same example. I drink tea, I like tea, and they drink coffee. Here the formula is slightly modified. If you check back the earlier formula, I am just going ahead with the earlier formula, we count the occurrence of two subsequent words with the previous word, the count of previous word here. Here it is almost the same, except that we are adding a plus 1 to it so that it must not become 0, and we are in the denominator we are having plus v, where v is representing the vocabulary size. Now when we take these three examples, this is S1, S2 and S3. For these three examples, the vocabulary is going to be the list of all these words plus milk, because we are going to count the milk also as per the question. So if you take the number of words as per this, it would be 7. I drink tea, like, they, coffee, milk. So total number of words here is going to be 7. And if we are taking the diagram, this is the same as the table that we mentioned last time, where drink tea the count is 1, like tea is 1, and drink coffee is 1. Now if we consider the probability of milk given drink, this is with smoothing technique. The smoothing technique, what happens is, we said earlier it was 0 plus 1 divided by, this one comes from here, and the count of Wi minus 1, it is 2 plus 7. 2 is number of times drink occurs, that is 2, plus the vocabulary size is here, that is 7. So it is be 1 by 9. So we can see that earlier this was 0, the same value was 0, but now it is actually, it is not 0 but 1 by 9. So it is minimal, saying that, so in order to avoid 0, we are incorporating this structure, this smoothing techniques, and this is called as a Laplace smoothing techniques. There are other smoothing techniques that are in the literature, but owing to the this course where we have only specific timings. I am not dealing into the different types of smoothing. You can go ahead and look with other smoothing techniques as well. But as such, the smoothing techniques is only used for avoiding the zero calculations. So now, having done all these structures, so far we have computed the probability and the foundation of probability along with the smoothing. Now we will move into how the words can be represented as a numeric form, because a computer cannot understand words directly just like human being. So humans understand the words. If I say, okay, this class is not that good, it is red in color, you can understand that. The language can be understood by humans. But how do we make a machine understand the words? And machines are very good at crunching numbers, as I said in the first class, but it is very bad at reasoning type. And where we can enforce the machine is that we can convert some form into numbers and automate it. So the question is, how do we convert into numbers? So for that, we would be using some type of representation techniques. It's called as the encoding, or in other words, we will take it as symbols, and which has no meaning for us right now, but we will make sure that a machine can understand something like with similar meanings can be got through numbers. So for example, meanings of cat and dog, it cannot be recognized by a machine, but we have to encode that in a certain way that a machine can understand. And similarly, the cat, dog, apple, tea, all these are going to be different. But how do we represent that as numbers? So one basic technique is we can represent it using a one-hot encoding, where one-hot encoding, it is word can be represented as a vector with 1 and the remaining all zeros. So let's take an example and do this. And for this, we will have a vocabulary. Vocabulary is nothing but a set of words that is coming inside the corpus. Corpus is the set of documents. So given a corpus or a set of documents, what we will do is we will extract all the unique words, and that will constitute the vocabulary. So the same example that we have taken before, say an example is, I drink tea like coffee. If you see the vocabulary, this is 1, 2, 3, 4 and 5. So there are 5 words here. Now how do we represent this as a numerical vector? Through one-hot encoding. As I, we are taking the first. So the number of words would be the number of bits. Each bit represents a word. So the vocabulary size, if V is equal to 5, the vector size is actually 5. If you see 1, 2, 3, 4, 5. So I represents 1 followed by 4 zeros. And drink represent, the second vector is 1, the remaining all are zeros. Tea, it is the third word, third position is 1 and the remaining all are zeros. Fourth is the like, where the fourth position is 1, the rest all is 0, and coffee is the fifth position is 1 and the other positions are all 0. So whenever we write as 1 followed by 4 zeros, it is only I. It is drink, it is going to be the second position 1. So this is the structure of one-hot encoding. So it's very simple and effective. So here each vector has a unique vector, and this word becomes a numerical form. But there are certain limitations. What happens if vocabulary is more? Suppose we take a corpus of around 100 words. I mean, reality, the vocabulary size is not going to be 5, but it can be 5 million. In that case, what will happen to this vector size? This will be humongous. And still it cannot, and because another difficulty is the sparse nature, where the sparse matrix is one where there are many zeros and only few ones. And if you see, each word is representing 1 and the remaining all 0. So consider a million a vector size, where at one position it is 1 and the remaining 0. Then it is sparse. And when it is sparse, again the computational, there is a difficulty. and it cannot capture the similarity or meaning of the words with one hot encoding. So how can we capture the meaning within this statistical site? Now, before going deeper into the encoding and the other part of the numerical structure, we will see how through a small program how to compute one hot encoding in Python. Here, this is in Colab. I have taken the same example where words is NP is for NumPy array, and I drink tea, coffee, where like is not given. There are only 4, just for example I have given here. There are only 4 words here. The vocabulary is consisting of 4, and here I have taken, see, and before that the libraries that I have imported is sklearn. This comes from scikit-learn. This is scikit-learn, and inside scikit-learn there is a function called one hot encoder that encodes the words. So here I am incorporating the NumPy library from Python, and in encoder we are calling this module. One hot encoder is called here, and the part output is given as false, so that we get only the required ones. And the vectors is we are transforming that the words, these are the words here that we are transforming into the vectors, and once we print the vectors, this is the bits that we have seen. So 1000 stands for I, 0010 stands for drink, 0001 for tea, and is for coffee. So these are the vectors for that particular words. Now coming into the back to our series, we were here, coming back to our series. Now the advantages of this one hot encoding is very simple, and it is a unique representation that I have said before, where each word has a separate vector, and it's easy to implement like how we saw in the Colab structure using Python. But the limitations, there are more. One is the sparse vector, where matrix everything becomes 0, and it's high dimensionality. High dimensionality in the sense, if the document size is more, it can run into thousands or into millions, then the computationally it becomes difficult. Again, the semantic meaning of it we don't understand. Suppose someone says the word as 0100, no one could understand. So how do we bring in those semantic meaning and the similarity between the words? Suppose tea and coffee, we know it is similar, it is a beverage type of it. So how do we account the similarity when along with the numerical structures? So considering these limitations, there is one more representation that we can talk about, which is TF-IDF and cosine similarity. Along with TF-IDF cosine similarity, something called as word embeddings. The first one is TF-IDF, where is this term frequency and inverse document frequency, which is used for converting the words into a numeric form with some kind of representation where we can reduce the sparse structure of it, and some meaning is involved. Like here, once we describe the formula, you'll be able to understand the meaning behind why it is called term frequency and inverse document frequency, and why such a kind of measure is required. See, TF is stands for term frequency. It measures the importance of word inside one document, while inverse document frequency measures uniqueness across all documents. So there are actually 2 kinds of formula here. One is term frequency, another one is inverse document frequency. So the left side is the term frequency. P is going to be the term and D is for the document. So this is given by number of times the term T appears in the document D divided by the total number of terms in the particular document D. In the inverse document side, IDF is given by the logarithm of capital N, where N is the total number of documents, by df of t, where number of documents that is containing the term T. And then we compute TF IDF, it is nothing but TF multiplied by IDF. So let's do an example here. So consider the three documents. For simplicity, I have given only two statements for this document. In reality, each of these documents may be maybe for 500 words or 600 words or even 60,000 words or even more. So this is just for our class calculation. I have given a very simple document to understand what happens between TF-IDF. So D1 is tea is healthy, I drink tea. The document D2 contains tea is popular, and documents D3 contains coffee is strong. So if you see the term tea, the term is particular word in the document or in the across the document. Suppose we say term tea is tea. So across these three documents it happens three times. The first time here, the second time here, and the third time here. And if you see healthy, healthy term occurs only in document D1, and popular occurs only in D2. And if you see the terms that is occurring in all the three places, all the three documents, the word is. This is occurs in all the three documents. Now, if you think does is going to play a role in understanding the language, it is not. Although it happens at all the three places, in all the documents there is, but it does not play a role in understanding the meaning out of it. So why don't we drop out these is and take only the remaining a word that is important. So that is the intuition behind this term frequency and inverse document frequency. So what actually it does is remove off these type of words or terms that is not important. The reason is it is happening across all the documents and it is of no meaning. So this can be removed off. So how do we do that? Using compute term frequency, compute inverse document frequency, multiply both, and if the value is very less, then we can remove that off, and that will be close to 0 when it is it's common across all documents. And if a word or a term is only happening at one document, then the value would be more, and that is termed as very important. So we'll take an example here. Is happens at all documents, appears here, and it is not relevant as such per se when we take the meaning. So to filter out this, we use TF-IDF, and when it is low score TF-IDF, it is common words. Common words indicate low score, and if it is important words, it is going to be high score, and that again we will be converting that to a vector. Now if we see TF-IDF of T, if we take T, the total number of terms in document D. So here I am considering only D1. From D1, TF-IDF of T is 2 by 3 multiplied by log of number of times, total number of documents. We have 3 documents, so it is 3, and number of documents containing the term T, it is 2, therefore 3 by 2. So the answer here is going to be when we calculate it is 0.117. Now suppose we calculate TF-IDF of is, then this is it's going to be 1 by 3 multiplied by log of 3 by 3. 3 by 3, why? Because is happening at all the 3 places. So 3 by 3 it is 0. So this is 0. So TF-IDF of is going to be 0. And TF-IDF of healthy, at healthy it is going to be 0.16. You can calculate it and check. So through this way you can see that wherever the word or the term is appearing at all the places, it maps to 0, otherwise it is going to be having some value. Now what are the applications of TF-IDF? It is used in search engines such as Google, and it is very much used in information retrieval. Why? Because we are discarding the most occurring term, thinking that it is not relevant to us. And it is used in document ranking, where we are taking only the keyword per se, keyword extraction, and based on that the ranking is prescribed. And similarly, we will be using in the text similarity, and we will be explaining that text similarity in the upcoming sessions. And it's used in the recommendation systems. The limitation, still it cannot capture the semantic meaning, like we do not know what that 0.16 is for. The word order, so which the sequence of words that is happening in the sentence, that is still not captured. The context with which the words and the sentence occurs. If you just give those numbers, we will not be able to explain the context with respect to those numbers. Say example here, king, queen are unrelated and cannot be expressed in numeric sense when we use only TF-IDF. Like we would be expecting something like, suppose king is 0.12, queen also should be somewhere around 0.13 or 0.14, but it will not happen in the case of TF-IDF. So are there any other measures that can be accounted? The answer is yes, we can do that. As a summary, in this session, what we have seen is, first we saw about encoding, and before that we saw the smoothing techniques, and then the encoding, one hot encoding, how we can convert the words into numbers in binary forms, where each word can be represented as a vector with ones and zeros, but it has difficulties like the sparseness and the meanings are not captured. Then we went into TF-IDF, where the TF-IDF captures the importance of words by filtering out the most occurring word in across all the documents. So that's with TF-IDF. Now we will move on into another measure called cosine similarity in the next session, where given any two documents, how with the vector size, with the vocabulary of TF-IDF, how do we compute the similarity in numerical sense. So that we will be seeing in the next session. Thank you.